Okay, let me share my screen and play.
Great. So, but forgive me, Wenbin, before you go ahead, for those who only just tuned in, why don't I just give you like a 30-second intro? You already did that yourself, but again, for those who came in late. So first off, welcome everybody to today's colloquium. Thank you all for coming. Hope you all are doing well. Yeah. Sorry, there's a bit of an echo. But today's talk is going to be delivered to us by Dr. Wenbin Liu, who is a Berg postdoctoral fellow at the California Institute of Technology. As the slide shown here suggests, he'll be talking to us about fast radio bursts from a theoretical point of view. But in terms of a very quick biographical sketch, Wenbin largely focuses on sort of the first principle angle of various sort of forefront-like physical phenomena that are being largely studied today, such as gamma ray bursts, tidal disruption events, and for sure fast radio bursts. Wenbin's biographical track began when he completed his bachelor's degree in Beijing University, in Peking University in Beijing back in 2013. And from there, he transitioned over to Austin, Texas, where he went to the University of Texas, where he performed his doctoral work in studying the emission mechanisms of fast radio bursts with Dr. Pavan Kumar, who actually came to and visited us within the last year, delivering a talk on fast radio bursts as well. From that point on, he transitioned over to Caltech ever since 2018, where he's been performing some good work over there. So with all that said, just so that we give him a bit more time, let's welcome Wenbin, and please go ahead and take it away.
Thanks so much for the introduction. So I would jump ahead. So here, I'm presenting all the works in collaboration with all these people, including Pawan, my advisor, and Tony at Carnegie, and Bin, and Ramesh, and Eli Waxman. So here's the outline. There are mainly three things that I want to get to the bottom. One is, what's the implication of, given all the FRBs that we know, what's the implication on the cosmological rates of these things? Where do they occur, and how often do they occur? And then I will look at the emission mechanism. What are the sources? What mechanism generated this very, very bright radio emission? And then at the end, if I have time, I will go through the polarization properties of FRB, which are also very, very important. So, so my plan is to include like one slide introduction, not too much, because I guess most of you have already heard many talks on FRBs. It's just introducing the phenomenon. If I were to summarize what an FRB is, it's really just a highly dispersed short pulse. The pulse duration is really the width over here. It's about a millisecond, but it actually it arrives, depending on the frequency, on a wide range of frequency. The arrival time is very different, up to about a second. So these are highly dispersed, following this (2⁻² arrival time prediction from cold plasma dispersion. On top of that, you also have there's some scattering broadening for this source. Some sources do not show this scattering broadening, which shows that at lower frequencies, the bursts are typically wider. And you can see that for this particular FRB, this dispersion measure, which is the measurement how dispersive this burst is, which physically means the Coulomb density of free electrons along the line of sight, is really large. It's much larger than what the Milky Way has along that particular line of sight. And this burst was really bright, something like 10 Jansky millisecond influence. So these are the introduction. So now after this has been, it was in 2013, now has been hundreds of FRBs. If one counts the CHIME unpublished ones, there are like close to 1,000 FRBs known, huge amount. And the main thing that one wants to know is how often do they happen in the universe? So here is a very simple plot that everybody can make. That the first thing you go to is the FRB catalog. There is a simple catalog online. You can download all the data, including the dispersion measure. By the way, the dispersion measure is dominated by the intergalactic medium. So it roughly measures the distance to us from the source. Of course, there are some uncertainties on how the host galaxy contribution and those things. There are some small amount of uncertainties over there. But roughly speaking, this horizontal axis shows the Milky Way subtracted DM, the excessive DM, roughly as an indicator of the distance of these bursts. And here is the fluence. Fluence is the integrated flux, how bright these bursts are. So these are very bright, observation of very bright ones, and these are very distant ones in general. And these ones on the right-hand corner are the most energetic, intrinsically energetic ones. So the first thing, you look at this, there are, I want to point out there are lots of uncertainties making especially the y-axis, the fluence. Many of these experiments do not measure the fluence very well, especially Parkes. Later on, I will explain why Parkes cannot measure the fluence very well, and CHIME as well. We don't understand the response function of the telescope at a particular line of sight. And so the first thing you look at this catalog, they are from all different telescopes. You look at, for different telescopes, there's a threshold, which is a fluence threshold, below which bursts are very scarce. So you can see that, let's say for ASKAP, roughly, below something like 20 Jansky milliseconds, ASKAP is not able to detect any bursts, like 1 or 2 maybe. And this DSA-10 was a project at Caltech. It detected 1, but it was only able to barely detect that one. And none of these bursts would have been observable by DSA-10. And here's for CHIME. So here's one of the very simple thing one needs to keep in mind. There is this fluence limitation. And on the other hand, if you look at it in the horizontal way, since the DM means the distance, there's also the volume. So at smallest DMs, you have to understand that so the telescope has a certain field of view. If you only look at the DM that are very small, you only restrict to the local universe where there is small volume, so you're not able to find a lot of bursts on this low DM side. Most of the, you can see that most of the bursts are at high DM side. And on the very high DM side, there is DM smearing, which is basically an intra-band dispersion delay, which will broaden your pulse. Later on, I will clarify what that exactly means. But there is a suppression of very high DM bursts on this very high DM side, which basically prevents this telescope from detecting them. There is a mystery if you first look at this thing. Why aren't there sources over here? You may argue that, oh, there are DM smearing over here, but DM smearing, which I will later on show, really kicks in for DMs above maybe 2,000, maybe 1,000, depending on the frequency resolution. The fact that, let's say ASKAP didn't detect bursts over here was a little mystery, to me at least. So another thing is that, so these bursts, let's say this burst was detected from Arecibo. This is one of the most famous FRB, which was a repeater. This one has seen thousands of bursts, mostly by FAST, this FAST telescope, which is the most sensitive single-dish telescope. It followed up this 121102 for, 50 to 100 hours and found thousands of bursts. So these bursts, including other telescopes as well, they cover a wide range of fluences. The brightest one can get to about 30 Jansky milliseconds. And of course, majority of them are very faint, like close to the very bottom, even below the plot here. So there's repeaters. Also, there's one more, this guy discovered by ASKAP. The first discovery burst was 200 Jansky milliseconds, extremely bright. And ASKAP followed it up for like 1,000 hours, didn't detect any repetition. But then later on, GBT was able to detect some faint burst over here. So you can see that these repeaters, they cover a very wide range of fluences. And this has implication whether the other ones, most of these are apparently non-repeaters, whether they are actually from repeaters, just luckily, one of these repetitions were seen, or they are intrinsically just one-off events. Okay, that I will clarify later on. That's what we got from these plots. So let's look at how the bursts are detected. So here I'm showing 3 different telescopes. This is ASKAP, and here is Arecibo and Parkes. So I'm going to look at the Arecibo and Parkes first. So these things are so-called multi-beam receivers. So there are many beams. Let's say, for example, the Parkes has 13 beams, whereas this Arecibo has 7 7 beams. One thing to notice that these beams, so here the circles meaning the half, so where the sensitivity is half at the maximum at the center of the beam. Basically, there are these gaps in between the beams. If an FRB, let's say, happened between one of these gaps, then the telescope is much less sensitive than if the burst were occur near at the center of each beam. So there are these gaps between them. And let's say for this particular burst discovered by Vikram Ravi et al., what happened is that it was discovered by this particular beam, but they were not able to localize precisely what the line of sight is. So you don't know what's the response function for this particular FRB. That's why the fluence was not well measured, because we don't know the response of the telescope. Same for Arecibo. However, as for ASKAP, this is the one of the mode that it observes. This is called the fly's eye mode. It has 36 different telescopes, individual telescopes, and the beams are packed such that they overlap. There's a half power circles. They overlap such that this entire array forms a uniformly sampled focal plane, which will be later on be very important in terms of inferring FRB rate, because from this uniformly sampled focal plane, you know how much volume this survey has gone into. In terms of depth, in terms of the distance into the universe, how much volume does this survey go into? Another very good thing is that, let's say for this particular burst and for other bursts as well, it was discovered by all 9 beams. So one can make use of multi-beam detection. Let's say this beam must have received the majority of the flux. Some of the other beams, because it was on the side lobe of other beams, the other beams may have received a little smaller flux. One can make use of the multi-beam information to actually pin down the location. These beam size are like 1 degree. One can actually localize these bursts much better than 1 degree. Actually can get down to about 10 arc minutes. So this relatively precise localization, making use of the multi-beam detection, and one can precisely know what is the response function of the telescope. So you measure the fluence extremely well. So here for this particular burst, this fluence, is constrained. This is a PDF for the fluence is really well constrained. Although some people, working on, stellar stars may not think this is very well constrained, but this is extremely well constrained. It's much better than any other, these bursts detected by Parkes or Arecibo, because it has this precise localization. So this motivates me to really. I told you that there are these all different samples. Let's first look at the ASKAP sample, which is the best described, and we know the surveyed volume as well. So it's very nice. So the first thing I looking at the ASKAP sample is to see whether the sample is what is the selection function, what is the fluence threshold above which the sample is complete. So this is a bit of a complex plot. Basically shows that the observed width of the bursts and the fluence. We know that the signal to noise ratio is proportional to the fluence divided by square root of the width. That's basically, the wider the burst is, the more noise you get into the receiver. So the signal to noise ratio drops. So there is typically what people do is they select there's a signal to noise ratio threshold of 9.5. So these bursts are selected based on this SNR. And you can see that the system, the entire sample, is roughly complete above about 50 Jansky millisecond. Below this, these bursts are very sparsely detected and it's unclear. But for these bursts, the reason why this is complete is that this is the only region where you can hide bursts without detection. And you can see that requires very long duration, let's say more than about 5 milliseconds. And those bursts are very rare. Inferred from the same sample. These bursts typically do not exist. So this sample is reasonably complete. So we can make use of these bursts as a kind of a fluence complete sample and look at, and also we know the volume that the telescope has surveyed. So this can tell us what is the rate, right? It's a very simple calculation one can do. So the first thing you do is that you make a little bit plots, because we know the DMs, we know the fluences, so you can make histograms for the fluence distributions. So here's the cumulative distribution for the fluences of the ASKAP sample. We know that it's complete below this 50. So we discard all those ones and look at these ones. So it looks like there is a little power law over here of something like a minus 1.5 index. The real mystery when I first look at this plot was really the DM distribution. As I told you, so DM roughly stands for the distance. So it shows that the DM distribution, roughly there is some power law of roughly some power law index of 1.5. It's something that's not typically, that people typically encounter. Just to remind you, for a standard candle, you get DM to the cubed, which is shown in the blue dashed line. Another thing that is unexpected, why there are no bursts detected above a DM of about 600. So the first reaction was that, oh, maybe this was due to DM smearing, meaning that the burst is really widened by DM smearing such that the telescope was not able to detect those. But it turns out it's not true. So here I'm showing for different DMs, what are the widening due to that DM. So let's say even if the DM is 600, it only widens the burst to maybe something 2 point something milliseconds. It won't get to like 5 milliseconds over here, such that you can enable fluence incompleteness. So that's really not the reason. So I concluded that this is really something really interesting. It's something physical. So what is the implication for this? So let's grab a piece of paper and do some very simple calculation just to show what it is. So first thing you say that, for a particular volume, what is the, we know that for a particular volume, there are brighter ones, there are fainter bursts. So let's say they have a power law distribution in terms of their energies, intrinsic energies. Let's also assume that there is a maximum energy, which later on I'll show it's a really key to explain this plateau in DM distribution. So from very simple calculation, one can easily say, one can easily predict what's the DM or the distance distribution, which you can easily find that for gamma is this power law index over here. If it is steep enough, if it is shallower than 1, then it's a standard candle because nearly all bursts are near the maximum anyway. But as long as you're not near like a standard candle, you find that this distance cumulative distribution, this power law index, to be 5 minus 2 gamma, which if you say this equals to 1.5 as observed over here, what you get is gamma is something like 1.7 or 1.8, right? And another indication of the maximum energy is that there is a maximum distance below which you can detect bursts. Beyond this maximum distance, no matter what the bursts are doing, ASKAP is basically blind to it. And that basically explains why there is a plateau over here. It flattens. There are no more bursts above this DM. So that's the key. And one can also work out the fluence distribution. One can easily explain with this introducing of this maximum energy, one can easily explain this fluence to the minus 1.5 behavior. So that provided a very simple analytic explanation. And of course, one can easily deduce gamma and Emax and the overall rates from this analytical calculation. But we did a little more sophisticated, a little more careful work by looking at using a Bayesian framework. It's also very simple calculation. So the first we do is that we assume there's a Schechter function, which most of these sources in the universe are like Schechter function anyway. So we assume there is a power law index and an energy distribution, and there's a maximum energy above which there is an exponential cutoff. We also included some redshift distribution of the overall rates. So these are rates in per gigaparsec cube per year. So there's Emax. So from now I'm gonna use this energy, this unit. This is erg per hertz, meaning that it basically comes from Jansky millisecond. If you multiply distance squared, you get this erg per hertz unit, which is really the specific energy, but I'm gonna call it E anyway. So one can predict what is the fluence and DM distribution. It's a two-dimensional prediction. It's not like this one-dimensional cumulative plot. It's really a two-dimensional plot because each burst has its fluence and DM. So one can predict both distribution, and one can construct a likelihood function based on the Poisson probability. And then these are the posterior. What you get, the most interesting thing is that there is this gamma. So gamma is constrained to be roughly 1.6 plus minus 0.3. So it's reasonably shallow. It's less than 2. I mean, it's shallow, less than 2. And there is also constraint on the maximum energy, although the arrow is pretty large. It's like plus minus 1 order of magnitude. But they are only in 20 bursts. These are the best amount of information that we can get from here. So here I'm plotting the, so from the ASKAP, from the posterior, I know the posterior of all of this. I can marginalize over all the things and then plot the volumetric density function. So this is the volumetric rate density, meaning that dn d log E as a function of log E over here, E meaning specific energy again. So here is the constraint on gamma, which is the power index, and then the normalization. Here's the normalization at 10 to the 32 arcs per second. That's reasonably well constrained within a factor of 3, or 3-ish, maybe 2. So reasonably well constrained. So the rate above this specific energy is this in the local universe. And here is also another prediction on the maximum energy, which I think it's a new thing. It also has got some physical implication. Here's my guess. So if you just take this energy and you convert that into a luminosity, because we know that the width, the frequency width is about a gigahertz and the duration is about a millisecond, you can easily convert that into a luminosity. It comes out to be 10 to the 46 arcs per second. From that, you can trace this wavefront back onto the surface of a neutron star, assuming that is from neutron star. Black hole is the similar. You can get the amplitude of the wave electric field, which turns out to be 10 to the 12 ESU, which is amazingly big. It's a big electric field, which is approaching this Schrödinger limit. So my hypothesis over here to explain this maximum energy is that above this luminosity, the reason why you cannot generate FRBs above this luminosity is that the electric field is so strong that it basically sparks Schrödinger pairs in vacuum. So this electric field cannot exist for a long time, actually much less than a nanosecond. So you won't be able to generate FRBs, according to my theory. I mean, according to this speculation or conjecture, you can say. So that's about this. The thing is that by the time we published this paper, we were not brave enough to extrapolate this rate all the way to the fainter ones. Of course, if you extrapolate, you find that the rate is huge. Can be very, very big. And I should have extrapolated, but I was too scared to do so. But later on, hold on. So, I'm gonna show one more before extrapolating. I'm gonna plot this maximum energy in this dm and the fluence distribution over here, which shows over here. So this, assuming dm stands for the distance, you can see that there is indeed a clear empty region where the bursts are lacking. So that I think is very physical. There seems to be a maximum energy, although the exact energy is not very well constrained. There's an 2 orders of magnitude uncertainty over here. So I can imagine if you can make the same plot with the chime sample with 1,000 bursts. I think one should see this lack of bursts over here very easily. But I haven't done that. I haven't seen a plot of that. So going back to the extrapolation, so I'm going to extrapolate the rate back to the lowest energies. So here's the extrapolation. Here's the ASKAP sample again over here. So if you want to extrapolate all the way to the lowest energy, first, by the way, I forgot to mention that these black dots with arrow bars, those are independent analyses. These are the range over here is based on the Bayesian analysis that, as I told you. These black dots are basically based on this one V over V max estimator. It's a classical estimator which has been used for AGN and GRB and all the things, which shows agreement. So basically, my Bayesian analysis is good. So now let's extrapolate over here to include this newly detected galactic FRB. You see that it's actually consistent with the overall trend of FRB rate. So the first thing you draw, the first conclusion you draw is that this galactic FRB is most likely just a continuum. It's just an ordinary FRB, but just with fainter, but a lot more of them in the universe. And another thing you can constrain is the polar law index. With this level arm, you can constrain the polar law index a lot better. It turns out to be something like 1.9 plus minus 0.1. This is a single burst with some Poisson errors. So that's the first indication. Another very interesting indication is that, so first I have to convince you that I believe this galactic FRB is from a repeater. It's unlikely that stare 2 or chime was just so lucky to capture this single burst within its lifetime. So I think this is a repeater. And here I'm showing this. This is also another repeater discovered by chime. This is a so-called periodic repeater, which contributes a lower limit on the rate because we know the distance, we know the volume over there. So you can see that repeaters really contribute a significant fraction of the known total cosmological volumetric rate. So I believe that at least a large fraction of FRBs are really from repeaters, not from these non-repeaters. It could be that these all are now they're actually repeaters, even though most of them we haven't seen repetition. So so that's so I think most of the FRBs are probably not from cataclysmic sources. They're just from repeaters, most likely magnetars, as this guy indicated. So that's for the on the total volumetric rate side. I also did some analysis on the chime sample, although you will immediately face the problem that the chime sample, I'm only looking at the chime repeater because the non-repeaters haven't been released yet. The chime repeater is a small number statistic, and there are lots of biases. Keeping all those in mind, what I can still do is the following. Again, let's assume that each repeater, because these are repeaters, each source has some power law behavior. It repeats more often on the lower energy side, which is shown by all repeaters as we know. It repeats more often on the lower energy side and less often on the higher energy side. I'm still going to call it gamma, although this gamma is a different index than this gamma. I'm still going to call it gamma because later on I show that they are actually very similar. If you say this is gamma, what will happen is that you can easily predict for single detection. Here is the distance distribution. I mean the DM distribution also. For repeaters, it's very different from a single detection sources. The DM distribution should have this behavior. The cumulative distribution, you can see that it's much more sensitive to this gamma, this 4 times gamma, the distance. If you can somehow measure the DM distribution of repeaters for some controlled sample, well-controlled sample, you can immediately infer what gamma is. So the first thing, so I make this plot of the DM distribution. I bin them. Of course, there is a small number of statistics, so I bin them into 2 different bin width by a factor of 2. But the universally, you see for different binning method, you see that there is a lack, there is an excess of high DM chime bursts. Basically, there are 2 very high DM chime bursts, chime repeaters, which are very surprising to me. Basically, if you put the other repeater 121102 at these distances, none of the FR 121102 bursts would have been detected by chime at all. So why chime was able to detect these repeaters, really detecting multiple bursts from these sources? So that has implication of this gamma. So there's a critical gamma, of course, and shown here, depending on whether most of the sources are dominated by high DM sources or low DM sources. It looks like they are dominated by somewhere in the middle. There is no consensus on what the gamma is. So I did a Bayesian analysis just to look at, just to require that chime detects 2 very bright, very high DM FRBs, repeaters. So here's the conclusion based on that. Again, you can constrain this gamma. Now I'm going to call it gamma repeater. So gamma repeater, the constraint on gamma is shown in the black solid line over here. It's very uncertain, but the fact that the dependence is 4 gamma over here, it has some power. So it constrains the gamma cannot be very shallow, cannot be extremely steep. So here is the chime constraint. And also I have shown you the ASKAP constraint from the ASKAP sample only. And here's the joint ASKAP and stare 2 constraint. You can see that they are roughly consistent. So the moment I showed this plot to Tony, which is one of the collaborators over here, he basically said, oh, probably these are all repeaters. So that's, at least at this moment, is my point of view on the entire FRB population. Let me see what I'm doing on time. It looks okay. So I'm gonna stop here and not stop completely, but pause here. And hopefully there are some questions over here already.
Yeah, we have a couple of questions. One is from Vicky, who's
Yeah.
asking if they're all repeaters. In Chime, we have published a different width distribution between repeaters and non-repeaters. Do you have any idea where this can come from?
The short answer is no. I cannot explain that. So my understanding is that Chime is really good at selecting repeaters. So the repeater sample is well selected such that they are the most active repeaters in the universe. Basically, that's what That's because Chime selected them as repeaters. So maybe there's some systematic difference between the most active repeaters and those ones that are less active. I'm saying that my point of view is that most of them are repeaters, but most of them are much less active than the Chime selected repeaters. That's my understanding. I'll probably clarify this a little bit with the next slide, but let me take the other questions. Thanks for the question.
I have a question myself. In the previous slide, you showed that the repeaters have a different DM distribution, but I didn't really understand why there's different dependence on gamma. Can you maybe elaborate a bit on that?
Yeah, it's very simple because for a single detection, right? The probability of getting a single, right now I'm assuming a Poisson wait time distribution. So for a repeater, you have to detect it twice, right? So this energy distribution has to be because this is the rate. If you have a repeater, if you have a repeating source in your field of view, this is basically says the probability of having a detection, right? Because this is a detection rate, right? So you have to square this because that's the detection rate squared because you want to detect it twice, right? And then there's a distance squared because there's a volume shell, different distance. So distance squared, and so that comes down to distance squared, and then this probability squared. So you get to the fourth power of this factor.
Okay.
Yeah, I can grab a piece of paper, although I didn't write the derivation here. It will be like one sentence derivation. I can easily show you over here. It was also in this paper. Sorry, I wasn't able to explain very well.
No, I can see it now. Yeah, very clear. Thanks. There is one last question from Mohit, who's asking how much your volumetric rate estimate depends on the host galaxy DM contribution.
Yes, that is a very good question. So for now, the way I'm doing Milky Way subtracted DM, I didn't subtract any host galaxy DM. So my expectation of the host galaxy DM, from the known localized host galaxy for some of these, some of these bursts are localized, is that it's something like it's like 100 or less, most of them. So it doesn't affect most of these things. So most of these, you can see that my DM distribution for the ASKAP sample, majority of them, maybe these ones will be affected, but the majority of them over here are not affected. It'll be a weak effect on them, at least within the current statistical uncertainty over here. The DM contribution of the uncertainty on the DM host DM is subdominant for sure. Thanks for your question.
Even if they go through a foreground galaxy?
Yes, even if that.
Okay.
A foreground galaxy would contribute maybe something like maybe 50 or something, and the probability is small anyway.
Okay, thanks a lot.
Should I keep going?
Yes, please.
Okay, so I'm gonna keep going. Before I switch to the emission mechanism, which I will definitely go very soon, I would look at already there is evidence that FRBs show a wide range of activity level. So this is partially trying to answer Vicky's question. Some of the FRBs are very active. So here I'm showing, because right now I'm assuming there is a power law repeating rate distribution. The fainter ones are more often, and then brighter ones are less often. So one has to pick a normalization. So I normalize this power law at 10 to the 30 erg per hertz. So so 121102, if you look at burst only above this energy threshold, it repeats roughly once per day. And for many of these ASKAP bursts, as compiled by James et al., one can show that from monitoring from extensive monitoring, they're actually much less active than 121102, even if we normalize at the same energy. So there's a wide range of activity level, which I'm saying that most of the chime repeater sample is really selective for those ones that are the most active repeaters. So they may be physically slightly different from those ones that are less active, let's say especially these ones. These are only upper limits. They may turn out to be very much below this 121102 because these are just upper limits. People aren't able to follow up for thousands of hours with limited telescope time. So that's that. I also constructed some, so there's a way to actually constrain the a distribution. So there's another very confusing, distribution of the activity level, which I may not go into them in detail. But if you assume FRB, some FRBs are much more active than the others. Let's say 12, 11, 2, and this 18, 09, 16 are very active among the most active ones. There are a lot of weakly active ones. So there's the distribution of the activity level, which I'm characterizing it by index Q. So one can easily convince yourself that the total repeating fraction of the chime sample, which I roughly know, but I don't know precisely, is about a few percent. It's basically over here. I'm showing in log here. One can constrain this Q, meaning how many more inactive ones or how many more active ones. And this level arm, chime has this power to constrain this the distribution of that. But regardless, the known chime repeating fraction, total fraction, already tells us this Q is about 2, maybe between 1.5 and 2.5. So most of the sources are very weakly active. So I guess those are the ones that are ASKAP detected, and maybe most of the chime singly detected sources. So there may be some systematics where the singly detected sources are just narrower, whereas the repeaters are broader. So that's my expectation. So I'm gonna go to the emission mechanism aspect. I think there was so much time spent on the cosmological rate. I hope people have followed up my discussion. So here is, so basically, so the most amount of knowledge we had is from this Galactic FRB because it's so nearby and there's an X-ray counterpart. So what happened was on April 28th of this year, there was an FRB detected both by chime and stare-2. Here's the plot shown in, it's the de-dispersed plot. You can see that chime detected 2 pulses separated by about 30 milliseconds, whereas stare-2 was only able to detect 1 of the pulses. This one, you can see that the frequency, if you go up to 1.3 gigahertz, the extrapolation meaning that the flux in stare-2 channel is very faint. So stare-2 didn't detect it, nothing surprising. But this one was co-detected by both instruments. There was an X-ray burst, coincident, actually very, very well aligned with the chime bursts and when the stare-2 burst. And this is a light curve for the X-ray burst. It lasted basically for something like 0.3 seconds, and with a lot of millisecond spikes measured by HXMT. So I want to argue that these X-rays are most likely from within the magnetosphere. This is because the total energy is about 10 to the 40 ergs, and this amount of energy won't be able to break out of the magnetic confinement of the magnetosphere for a magnetar. We know this was from a magnetar. So these X-rays are most likely from within the magnetosphere. And a very, the minimum model is that the FRBs are also from magnetosphere. This was also supported by that the chime and stare-2 arrival time, they're perfectly aligned within actually less than a millisecond, perfectly aligned. So all these frequency emission from all these frequencies, they're narrowly, temporarily emitted at the same time from this roughly the same spot, basically. So that argues for a magnetospheric emission. Of course, every time when you have these new observations, you throw away all your past assumptions and past work and restart all your calculation, and just to look freshly, what are the models that can survive? What are the models that work the best, right? So here is, I'm gonna first look at this event from a top-down version, from a top-down approach, meaning that I approach from the observer's point of view. I know there's a luminosity, so here's the luminosity for FRB, isotropic equivalent luminosity, 10 to the 38 ergs per second. And it's in gigahertz frequency, and it's most likely from magnetosphere. So the most likely scenario is that it's from some curvature emission. which makes sense for gigahertz waves. So in order to get that, what you need is that the Lorentz factor of the particles is about 100. This is rho is the curvature radii in units of 10 kilometers. And it has to be coherent because the luminosity is so high. Each individual particle, here's the luminosity for individual particle. This is so big that each clump, I'm showing this clump over here, these are clumps of particles. They have to radiate coherently. Each clump contains about 10 to the 21 particles in each clump. And one can easily estimate what is the cooling time, because this is the total kinetic energy of the clump divided by the luminosity of the clump. This is a beaming corrected total power. And it turns out to be the very, very short. So this clump cannot sustain itself radiating for more than a nanosecond even for a very long time. So this clump, so whatever powers this clump, there must be an electric field which keeps pumping energy into this kinetic energy into the clump. So one requires that the system, this plasma, local plasma, must be charge starved. Otherwise, from the Maxwell equations, if it is not charge starved, you end up having currents with no electric field. If it is charge starved, meaning that the plasma is incapable of supplying enough current, you develop this displacement current, which was proposed by Maxwell. And you have this electric field, which is parallel to the B field, which can do work and accelerate particles and radiate. So the constraint is that the local density must be less than this, although we don't know what this is. Later on, I'll clarify what this is. And also, the density must not be too low. If it is too low, you won't be able to generate clumps of this 10 centimeter size. So you have to require the local plasma frequency to be more than gigahertz in order for such clumps to exist. So those are very general constraints from this curvature emission mechanism. So let me also do from the bottom-up approach, because we know there are X-rays irradiated from the system. So what happens is that these X-rays are believed to be from near the surface of a magnetar. What happens is that, let's say if you have a trigger near the surface of a magnetar, what happens is that it will generate oscillations near the surface, which is called the crust of the neutron star. The crust has very large pressure, which is electron degeneracy pressure, and there is very strong gravity, such that the most likely way you can excite waves within the crust is this so-called shear waves, which looks like something like this. So the shear waves has the good properties that it does not involve any compression. So the pressure forces doesn't play a role, because compression is really difficult to compress anything with very strong degeneracy pressure. And it does not, because this shear waves is horizontal, you don't need to overcome gravity. So this is the easiest wave you can excite. So we believe that there will be shear waves associated with the X-ray burst, looking like over here. Imagine that there are magnetic field lines anchored on the surface. So the foot points of the magnetic field lines will be shaken by this horizontal shear waves. So that will send Alfven waves into the magnetosphere. And here it is. Here I'm showing in green dashed line is the shear waves, which propagates from where the trigger point and all across the entire neutron star. And there will be Alfven waves launched into the magnetosphere. This cannot be avoided. It has to happen. And it carries quite a significant amount of energy, because one can calculate what is the transmission coefficient, what fraction of the energy of the shear waves can get into the magnetosphere as Alfven waves. One can easily calculate that this by impedance matching, that a large fraction, order unity fraction of the shear wave energy will be transmitted into the magnetosphere. What that does is it will generate a pair plasma, which will Comptonize, will radiate in hard X-rays. And that explains the X-ray emission over here. And when the shear waves propagate all the way to some polar regions close to the poles, where the field lines can extend to very large distances, what will happen is that these Alfven waves can get to very, very large distances. And one has to look at the propagation of the Alfven waves through the entire magnetosphere, right? Because it carries significant amount of energy, as large as what the X-rays contain. This amount of energy goes as follows. So imagine you have a wave packet. This packet, expands. It follows Alfven waves follows the group speed is along the B field line. So it follows the magnetic field line, and the wave packet will expand. So this is the transverse wave number, and then the wave amplitude will decline. So one can easily estimate what is the current density needed to supply this Alfven wave. One can easily say that is, it's curl B. And this drops as this. There will be a point. So these Alfven waves will propagate to the outer magnetosphere, much larger than the neutron star radii. It will become charge starved once this condition is satisfied. Once the local plasma density is sufficiently low, it will be charge starved. What will happen when it becomes charge starved is that displacement current displacement current is basically an electric field will develop. And this electric field would in turn accelerate charged clumps and then radiate FRBs. At least from this bottom up version of the story, this seems to hold up. So that's this. From that, I can already present a unified picture. I'll pause for questions after the following 2 slides, and that's probably the end of the talk, hopefully. And then, so from the charge starvation radius, let's say if you, so first thing, we don't know the charge density distribution in the magnetosphere of a magnetar. One don't have a first principle calculation for that, but one can still make some predictions. Here is, let's say, assume the charge starvation happens at a distance r to the center of a neutron star, and r is in units of 10 kilometers. One can calculate what is the charge density at the charge starvation radius given by this charge starvation criteria, and normalized by some parameter. This is the transverse wave number at near the surface of a neutron star, which is quite uncertain, but roughly is along this range. These are shear waves. This is roughly given by the shear wave speed divided by the shear frequency. So one can easily predict what is the luminosity if the observer happened to sit along within this cone. The observer will see the FRB beamed along this cone. This is roughly the luminosity depending on the amplitude of the initial perturbation at the foot point and the transverse wave number. These are uncertain parameters, which later on will enable a wide range of luminosities to be generated. And those are other predictions like the beaming angle. It has to be sufficiently close to the poles, not very close though, so such that the B field can extend to large distances to allow charge starvation. And FRB duration is basically given by the shear wave propagation. And then one can generate narrow structures, narrow frequencies, and one can also work out the luminosity ratio for FRB and the X-rays. A little small fraction of the energy actually gets into the FRBs. And one can also predict linear polarization. So that's this one. And this slide, which would normally be my final slide, is the entire parameter space. As a function of the initial perturbation amplitude for the Alfven waves at the foot point and the charge starvation radius, which both of them we don't know. These can be controlled by the local condition. As a function of this, I can predict what the FRB luminosity is, given some good, given that the observer is along the line of sight of the bunch, of the beaming angle of the bunch. You can see that this model works for a wide range of luminosities, for all the way to 10 to the 36 erg per second, all the way to the very brightest FRBs known. So one thing to notice that the brightest ones are actually limited by this Schringer pair production, as I mentioned earlier. There's another limitation, which is where the Alfven wave become nonlinear. And that probably I won't have time to go into that in detail. Basically, the Alfven wave is stronger than the magnetic field in the magnetosphere. Basically, the entire magnetosphere is blown away. There will be no more curvature emission. And there are other constraints over on this side. So those are the entire parameter space. You can see that it can explain the Galactic FRB as well as some of the brightest ones. This one was detected by DSA-10, was one of the brightest ones, localized. And this is the range of FRB luminosities known from this R1, the first repeater, and the third repeater known ever. And you can see that those are easily explainable by our model over here. So, so this is a summary slide. I'm going to leave the summary slide and take questions. And later on, if we have additional amount of time, I have 2 more slides addressing the polarization. Maybe we can go through that, but let me take questions for now.
Yeah, thank you. Thanks a lot. Really interesting and clear talk. I see there is a question from Ziggy, who's asking how well are the neutron star disturbance is constrained? For example, the occurrence rate and the amplitude?
That's a very good question. The answer is not constrained at all. Because most of the energy comes out in the X-rays. That's what you typically normally expect. Because most of the surface area of the neutron star is really covered by closed field lines. These closed field lines, they don't extend to very large distances, so no charge starvation will happen. So this Alfven waves is going to bounce back and forth for many times. Each time it takes maybe like a few microseconds, and it just bounce back and forth multiple times. Eventually, they will cascade into smaller and smaller scale turbulence, and then they will be dissipated. So this amplitude really comes down to what triggered these activities, and it's really one has to see the X-rays to have some guess. Well, roughly speaking, if you say this X-rays correspondingly is like isotropically emitted from a surface of a neutron star, you can have a very extremely rough though amplitude estimate. Roughly comes down to 10 to the 9 Gauss for the Alfven wave over here. So that's for this particular galactic FRB though. For a cosmological FRB, we don't know at this point. Good question. Thanks.
Okay, thank you.
So at this stage, I recommend that we let people who have questions feel free to unmute and actually ask the questions themselves. But we ask that folks try the best they can to use the hand raising feature so that we can sort of do this in an ordered way. That being said, Vicky did actually post a question first. So before we get to Matt, why don't we have Vicky go ahead and ask her question?
Okay. So I had one question is, do you have a robust prediction for whether the X-ray burst or the radio burst should come first? And then I had another minor question. Some slides you say the maximum luminosity should be 10 to the 46, but then on another slide you had 10 to the 48. So I'm a little confused by that.
Okay, let me answer the first question first. Yes. So hold on. So you're asking about the X-ray?
Should it always be the case that one comes, that the X-ray comes before the radio, or the opposite?
Yes. Thanks so much. So this model predicts, I can only tell you that how rapidly the radio emission is going to get out. Basically, this trigger and then some propagation time, which is about a millisecond, and then this radio emission is basically coming out at speed of light. Alfven wave propagate at speed of light. So radio waves should come out very soon after the trigger, maybe after one millisecond or so. And the X-rays, there is some uncertainty on the X-rays, which I'm not able to tell right now. I'm still working on it. Even yesterday, I'm still doing some calculations. It depends on, there is a quantity called diffusing time. We know that there will be a fireball. It's a pair fireball, which will be hugely optically thick for X-rays. It depends on at the skin of the fireball, how rapidly the X-rays can escape and how fast the energy can be drained by the escaping X-rays. And that, my rough estimate, I don't have like a physical understanding of what sets the opacity and how the diffusion time is set, but I think that can be of order millisecond, at least from known X-ray bursts. So I personally expect them to be contemporaries, but the X-rays may be slightly lagged, but not much. So that's my conclusion. So the other question was on the maximum luminosity. So the maximum luminosity was inferred. So let me quickly go back to the maximum luminosity. Thanks very much. I think it was confusing as well. So maximum luminosity over here was constrained observationally. So there's no assumption made on the maximum luminosity. It's 10 to the 46 with the large error bar. This is a 1 sigma error. So maybe 10 to the 45 to 47 erg per second. And also, I'm only constrained the erg per hertz, and one has to get back to the luminosity. One has to look at whether it's a gigahertz width and the millisecond duration. And there are those uncertainties. I think it could be a slightly larger or slightly smaller. And the prediction later on was really for one specific model, which I have put the parameters over here. There are some parameters. Let's say if the B field is different and if the shear wavelength is different, there are some wiggle room over here. The main goal is to show the width, the breadth. Like over about 8 orders of magnitude, this model can explain a wide range. But precisely what the maximum luminosity should be, I think there is some room there over there, but I cannot be more precise than that. That's my current limit. Thanks for your questions.
Thank you.
Yeah, I see that Robert has a question, if you want to ask that directly. Well, I can ask it, if not. What does the unified model predicts in terms of periodicity?
No prediction on the periodicity. It depends on when does the trigger occur. And that, I suspect that, I don't know. I suspect that doesn't have any periodicity. If one has to learn from the galactic magnetar, those SGR bursts, there doesn't seem to be any periodicity. So that to me is a mystery, complete mystery. It could be precession. I think that seems to be the best model so far of this pole. The pole, it may be precession, but I'm not sure because I haven't worked on that. Thanks.
Okay, thank you. I see that Matthew has a question.
Yeah, I was wondering if the comptonized hard X-ray emission had a fixed ratio with the radio flux, or whether or not that varies by a large amount.
Very good question. My answer is that it will vary by a large amount. It can, in principle, vary by a large amount. Let me walk you through how this ratio is obtained in our method. It's extremely rough, though. It's really an order, not even an order of magnitude, very, very rough. And what happens is that you have a trigger, and the trigger, the propagation of the waves, of the shear waves propagates through the surface. There will be losses along this propagation. What happens is that these shear waves, they propagate in the following way. They actually, the crust has certain height. They actually bounce back and forth between the upper boundary and the lower boundary of the crust. They bounce multiple times. Every time they reach the very surface, there will be a lot of transmission into the magnetosphere. That will later on become X-rays. So there will be a lot of losses along the way by the time you get to the near the poles. So there will be a lot of losses. Very rough estimate is extremely rough. It may be like 1 part per 100, 1 part per 1,000. Maybe maybe only arrive at the poles. A very small fraction will arrive at the pole. Even that amount of energy, I mean, isotropic equivalent energy, getting to the poles, it will be diluted because of the Alfven waves. The bundle of this Alfven wave packet will expand as you go to large radii. What will happen is that the isotropic equivalent energy, as observed over here, will have an additional reduction due to this divergence of this bundle by a factor of 10 or so. So there will be some dilution over here, and there will be some, you can see from the way I'm talking about, the way I walk you through, you can already see there are large of uncertainty over here. I wouldn't surprise this will be turn out to be, let's say, 10 to minus 3 or 10 to minus 5. I wouldn't be surprised. If it's 10 to minus 8, I will be very surprised. Thanks.
Thank you.
We have one last question from Daniela, if you want to ask it.
Sure. So my question was, have there been any attempts to stimulate FRB populations, but starting at this unified model level?
No. Basically, this unified model can predict for a particular FRB. If you tell me what is the kind of perturbation strength and where the charge starvation radius, I can roughly tell you where the luminosity is. But it doesn't have the power to predict the rate or the distribution in amplitude. How frequent would a magnetar have a disturbance of a larger amplitude versus a smaller amplitude? That this model has no prediction along that line. That depends on how these things are triggered. These things are most likely magnetic reconnection. This has nothing to do with the FRB. They're just near the surface of a magnetar. They just maybe some trigger disturbance just happened over there. That So I don't expect anybody can take this model and predict for the entire population in terms of rates. Yeah.
Thank you.
Thanks.
Yeah, I think that was the last question we have.
So it looks like that's that's it. Or maybe I don't have time to go through the polarization. I think that's fine. I mean, if you guys still wonder.
I do have another question, which is, what do you think about polarization?
Very nice question.
Very nice question.
Thank you.
Yeah, very
So
good.
I have 2 slides extremely quickly on walking you through the polarization. It's a very simple concept and it's been well known. I'm actually writing a book with Shri, and I basically wrote all these things in the book. It's very simple physics. It basically comes down to this propagation of electromagnetic waves in the magnetosphere. Sorry for the equations, but these are very simple equations. It's just a wave equation from the Maxwell equations. Assuming that the B field is very strong, which only allows particles to move along the B field lines, you can write the current as a parallel current, which ties to the parallel component of electric field. Parallel, I mean parallel to the B field. There are only 2 modes that can propagate in the situation where the plasma frequency is much higher than the wave frequency, and the cyclotron frequency is infinite, because the B field is very strong. There is this Alfven wave, which I already talked about. There's X mode. FRBs, in order to escape, it has to be the X mode. And actually, Alfven waves are not emitted by these charge bunches. So this X mode radiation, one can easily solve this in the inhomogeneous plasma. Right now, the magnetosphere has some inhomogeneity, but it's weak. In terms of that, the inhomogeneity happens on the length scale much longer than the wavelength. Wavelength is about 10 centimeters. The inhomogeneity occurs on something like 10 kilometers or longer. So one can decompose the solution into a homogeneous solution, which is the X mode, which is perpendicular to the KB plane, shown over here, X mode, which is very easy. It just stays perpendicular to the local KB plane all the time. There's some weak inhomogeneity term, which the amplitude of that is given by the following. Very, very simple, straightforward. This given by the iconal approximation. And this is the length scale over which the B field varies, which is also the length scale over which the KB plane changes, because that's what the wave care about, the polarization care about. And one can calculate what's the current density associated with this, right? Given there's a relation between them. And there will be a polarization limiting radius. The wave would propagate as a straight line all the way, and there will be a point beyond which there is insufficient amount of plasma to turn this electric field to be perpendicular to the KB plane, which can be obtained in two ways. One is that this has to be small compared to this, such that it stays perpendicular, which this is in the pulsar case, which people have already been very familiar with, and people have concluded that this polarization limiting radius is such in the magnetosphere, in the outer magnetosphere. Whereas for the FRB, since the electric field of the wave is so strong, this actually dominates. This term actually dominates. So basically, when the particle number density is less than what's required for the current density, you cannot sustain such a current anymore. It basically becomes a vacuum X mode propagation. So that's in the FRB side. On the FRB side, what will happen is that there will be one can easily calculate the charge starvation radius. Roughly estimate, but reasonably easy to calculate. It turns out to be much larger than the neutron star's radius and much less than the light cylinder for a magnetar, which is slowly rotating. And what will happen, the prediction is that the polarization angle, so I'm showing that the electric vector stays perpendicular to the KB plane. Here's the K, B is the local K, local B. So it stays perpendicular to the KB plane all the time until the polarization limiting radius, and then the polarization is frozen. So towards the end, the predicted polarization is perpendicular to the magnetic axis projected on the sky. That's it. That's the prediction for the polarization. And of course, the magnetar will rotate, so there will be some polarization angle changes from burst to burst. And that's the prediction. That's all that there is to say. Thanks.
Yeah, thanks a lot for the talk again. I think we need to close here because you have the meeting with the grad students in like 5 minutes. Just to remember, a reminder for all the grad students here.
Thanks everybody for listening.
Thank you. Very nice talk.
Yeah, many thanks, Wenbin. That was terrific. Thank you.
Thanks so much.
Take care.
Should I stay or should I join the other one?